two uh, talks in this session. The first one will be an oral presentation by a young researcher, Saptaswa Ghosh of IIT Gandhinagar. Saptaswa, are you there? Yeah.
Yes, yeah.
Saptaswa will be talking about observables in classical gravitational scattering from worldline quantum field theory, a case study for scalar tensor theory. So if you are ready, Saptaswa, so you may start. If you require, I may remind you at the beginning of last 5 minutes. Okay, thanks.
Okay.
Over to you.
Okay, so first of all, thanks to the organizers for giving me the opportunity to present my recent work. And the title of my talk is Classical Black Hole Scattering from Worldline Quantum Field Theory, a case study for scalar tensor theory. And this talk is basically based on our recent work with my supervisor, Professor Arun Bhattacharya, and my collaborators, Saunak Pal and Devodina Ghosh. So in a classical black hole scattering event, there are some parameters will be there. So the parameters are masses of the black holes. There might be some there is something called the impact parameter, and there might be some other theory parameters also. So there are three main observables, and one is impulse, that is we are studying some scattering of some black holes, and the main observables are basically impulse, that is the change of this initial momentum of the black holes, and other is the spin kick, that is if the black hole has some spin, then the classical spin may change, that is something called the spin kick, and we have another observable that is more important, that is radiation or waveform. So the bigger goal is to constrain the theory parameters. If the theory has some parameters, then the bigger goal is to constrain the theory parameters from gravitational wave observation. Okay. So classical black hole scattering actually can be treated as some limit of quantum scattering amplitudes. And to explain this, there are mainly two ingredients there. One is the bulk gravitational action, that is maybe for Einstein's theory, it is basically Einstein-Hilbert action. And there are some matter action. And the black holes are actually modeled by this matter action. So for Einstein-Hilbert action, for Einstein gravity, the bulk action is basically Einstein-Hilbert action. This with basically the R is the Ricci scalar, and the matter action is basically we take as a complex scalar field theory, which is non-minimally coupled with gravity. And here black holes are basically some kind of avatar of this matter field phi. Okay, and as the impact parameter B is very large compared to the individual curvature scale of the black holes, so we can in principle treat them as point particle. So a black hole scattering event, as I already mentioned, that can be formulated using standard scattering amplitude techniques, and we wish to investigate this following process. That is, we have two black holes scattering off, and we might have some radiation also. And this radiation is basically nothing but the gravitational waves, and maybe for Einstein gravity, it is basically gravitons. So it has been shown that the result from scattering amplitude techniques initiated by Kosovar and his collaborators, and further generalized for the speeding case by Diankelis, Novichkov, and Gonzo, matches with the standard worldline techniques such as post-Minkowski and effective field theory by Rafael Porto and Gregor Kalin and his collaborators, and by taking suitable classical limits. But the link between two different approaches are first illustrated by Plevka, Mogul, and Steinhoff in 20, and later in Damagard, Hansen, Plate, and Vanov in 23. Okay, so the question is how these two different approaches are connected. So to understand, and they are basically bridged by the way back to Feynman by Feynman-Swinger proper time parameterization. So to understand the link more precisely, here is the key ingredient is a graviton-dressed massive scalar propagator. So the matter, we already take the matter action to be the complex scalar field, non-minimally coupled with gravity, and the graviton-dressed propagator satisfies this condition. and G is the Green's function, this propagator. And this is not like just a propagator in flat space, because we treat the scalar field to be in some background G, that is the gravitational field. And one can in principle compute the Green's function or the graviton-based propagator by perturbatively in G. I mean G, if we expand G as a fluctuation around some flat metric, then we can perturbatively compute the Green's function there. Okay, and the gravitationally dressed scalar propagator has worldline representation, has some worldline representations that is first demonstrated by DeWitt and later by Bekenstein, Parker, and Larmor in 79. So the Green's function can be treated as, in quantum field theory, the Green's function can be treated as the 2-point function. And if we compute this 2-point function, we may, in some swing Feynman proper time parametrization, we may have some integral over some worldline. Okay, so here we see that the integration, the path integral is over the matter field phi, but it has some representation, like we have some integral over the worldline, and we have some action. And if we carefully see this action, this is nothing but the point particle action. And along with the point particle action, we have some ghost fields. And because of this non-minimal coupling, we have some term that is proportional to R, which is scalar. But and these A, B, and C are sometimes called the Lee-Yang ghosts. And that is, but as we are focused on only the classical computations, we can ignore them because they only appear in the in quantum loops. But to draw connections with S matrix, that we are actually considering some scattering event, so we have to do something with S matrix. And the S matrix is related to the 4-point function there. If we don't have any external radiation field, then we have to concentrate. We have to concentrate on this 4-point function. Okay, and this 4-point function can have some path integral representation. And if we integrate over the matter field, and we will get this type of this type of expression where we have the path integral over the bulk fields, and this path integral over the matter field will give the dressed propagators there, because we already defined the dressed propagators here. And now here we can use the worldline representation of the dressed propagator there and put it here. But we are not finished yet, because we need LSJ reduction to further connect the 4-point correlation function to the S matrix. Okay, so in a general scenario, we are also interested in where we have some external radiation there, and for this case, we concentrate on the 5-point function there, where we have the 4 scalar fields there and the external H mu, I mean the graviton field. And the S matrix is followed by LSJ reduction, where we have this path integral over the and this is the 5-point function. In after integrating over the matter field, we have some dressed propagator there and exponential weighted over some bulk action, which is for Einstein-Hilbert action, which is for Einstein gravity. This is just Einstein and Einstein-Hilbert action. And see, in the above path integral, by construction, there is no virtual scalar loop. That is, matter loop never appears. And while doing the path integral, we ignore the graviton and the scalar graviton mixed loops to ensure that we are working in the classical limit. And these computations are computations leads to something called the graviton Born type diagrams. And now we use the worldline representation of the gravitationally dressed propagator into the S matrix to find out what is the worldline representation of the S matrix, to put by putting the worldline representation of the dressed propagator here. Okay, but see, in this expression, it's kind of a action with action of a point particle, but the integral region is some 0 to some finite time t. But what has been shown is that definitely in order to define the S matrix, one must impute the external legs and put them on cell. And what has been shown in this paper by Plewka, Mogul, and Steinhoff is that if we put the external legs on cell, then it amounts to eliminate the T integral, that is this finite T integral. Sorry. this T integral, and the integral region is now 0, 0 to infinity. Okay, and this is nicely done in this paper. And now we have the S matrix, which is basically nothing but the integral over the bulk fields, and we have the two dress propagators in momentum space. And as we intend to do the calculations in momentum space, so we actually, this FC is nothing but the momentum space representation of the dress propagator, but we put the external legs on cell. What we see is that we first have some integral over the field configurations. Now we transform it to the integral over the word lines. So the word line path integral is now defined as follows, where we have some integral over the word line and the Lee-Yang ghosts are there. And what has been shown is that this path integral, this word line path integral here is actually related to the on-cell dress propagator. Okay, and we see, and the path integral can be eventually computed using some perturbative scheme. And here we see that X is also the word line is also a dynamical field. So we have some correlator, the 2-point functions. So we expand the we expand the word line as some background field that is basically nothing but when we have in infinite past, we have some straight line trajectory of the black hole before the scattering process. So we expand the action around some straight line trajectory in X and some flat background for G. So from the kinetic term of this action, we can eventually compute what are the 2-point functions there. And we see for Lie ghosts, there is no derivative there. So they are ghosts are basically non-propagating, but we have some propagating degrees of freedom, which is basically the fluctuation. Here x mu, we write x mu as some b mu plus v mu sigma plus z mu, where z mu is basically the fluctuation over the straight line background. And in classical limit, in principle, one can define the iconal phase, and which is given by this. We have this S matrix, and we took a Fourier transform over the impact parameter space. Then we get the iconal phase. And what has been shown is that the iconal phase is exactly related to the partition function of the word-line quantum field theory. But the partition function is defined as follows. We have integral over the bulk field, that is the graviton, and we have the integral over word lines and the action. And in the action, we have the bulk gravitational action as well as the point particle action. And we will definitely ignore the Lie-Yang ghosts because they actually come to in the quantum loop level. So what we see is that unlike usual quantum field theory, here word line fluctuations are also propagating degrees of freedom. We have some path integral over the word lines. And the iconal phase can be computed by summing over all possible tree-level diagrams, connected tree-level diagrams. Okay, so in word-line quantum field theory, this is the key ingredient. The partition function is the key ingredient that you already defined, and the partition function can also be computed perturbatively by expanding the propagating degrees of freedom around some background field. So the key idea is the physical observables, that is the impulse or spin kick or waveform, can be identified as an expectation value of the operators in word-line quantum field theory. So if we have some operator in word-line quantum field theory, it is O, the expectation value can be computed by this formula. And the above path integral, this path integral can be computed perturbatively in momentum space using usual Feynman diagram techniques. And we always do all calculations in the classical limit, that is the h bar tending to 0 limit. So we only compute the tree level diagrams there. So the formalism in principle can be applied to beyond GR theory also, and for spinning black holes also. Yeah, and for spinning black holes, there are another word line degrees of freedom, that is something called the word line superfield. but I will not talk about it. So in the context of general relativity, the study has been exhaustively used and in higher PM also in these papers. Okay, so what and in our paper, in the recent paper, the study has been extended to the beyond GR theory, namely the scalar tensor theory. So the need is already mentioned by Laura, that in general relativity is thought of one of the most successful theory describing the classical dynamics of the gravity, although it has some problems, like it cannot explain the late time acceleration of our universe or the phenomenon of dark matter or dark energy. So we need something beyond Einstein. So the way so the way to modify general relativity is that we can add some higher curvature terms or add some degrees of freedom, like extra scalar degrees of freedom or gauge degrees of freedom. So the simplest modification is to add scalars. And not only the phenomenological reasons, so from low energy EFT point of view, the Einstein section has some natural generalizations of this, like where we have the higher curvature terms as well as the extra degrees of freedoms there. Okay, so this is the simplest scalar tensor model, and this action is written in Jordan frame. And if we transform it into the Einstein frame by conformal transformation, it can have this kind of action. And all the observable computations are done in the Einstein frame because it is easier to do it in Einstein frame. So here is our model where we have the Einstein-Hilbert action, and we have some massive scalar field and some phi cube and phi to the power 4 interactions are there. So similarly, as I mentioned, that any observable is related to WQFT one-point function. So the waveform, that is the radiation, is basically related to the one-point function of the external gravitational field. That is, for our case, phi is basically extra degrees of freedom. That is, we have some one-point function of h mu nu and one-point function of the scalar field phi. This scalar field is different, and the impulse, that is basically the change of momentum, is basically related to the one-point function of the world line fluctuation. So more specifically, the impulse can be computed using this formula, and where we have some on-cell conditions there. And the radiation or waveform is related to the one-point functions of the bulk fields. That is this. Okay. Okay. So the question is how we can couple the extra gravitational field to the extra degrees of freedom phi to the world line. So the modification is that in world line, now the mass of the black holes are not constant. It is actually function of the extra degrees of freedom phi. And eventually we can expand the mass as a function of phi by choosing some background there in this way, but we expand it in for around phi equals to 0. And then we have to identify what are the Feynman rules for bulk interactions. The Feynman rules are trivial, like using normal visual quantum field theory. But when you have some interactions of the bulk fields with the world line, then the things are tricky. Because see, in the bulk interaction vertices, the full momentum is conserved, but in the world line, this is basically something lies in one dimension. So only the energy is conserved there. So which is basically, you can say, which is basically we are doing some calculations in classical level. So because of this, only the energy is conserved in this on this world line. So this is basically the reason why we have some loop integrals at classical level also. So we identify the Feynman rules by expanding the action in difference orders in Z, that is in the fluctuation. So once we have the Feynman rules, so we from the kinetic part of the action, we can identify what are the bulk propagators and what are the world line propagators are there. Okay. And the world line vertices, as I mentioned, can be computed different orders in Z. Okay. And these are the worldline vertices for scalar sector, at least for scalar sectors and scalar graviton interaction sector. And these worldline vertices are basically contributes to the 2 p.m. level, up to 2 p.m. level, 2 post-Minkowskian level. So when you compute impulse, so we compute impulse up to 2 p.m. and we have some 16 or 17 diagrams there, and these are the diagrams. So the diagrams are computed by usual Feynman diagram techniques. And for example, we can see this is one of the diagrams. So it is always good, and see we have some delta functions there, because in these world lines only the energy is conserved, and from this fact the delta functions comes. Okay, and when we have these delta functions, we see that the four-dimensional we have four-dimensional Feynman integral, but using these delta functions, the Feynman integral, four-dimensional Feynman integral basically reduces to two-dimensional integral. And it is always good to choose some frame to do this integral, and here we choose the frame of the black holes. And here is the parameterization of the black hole velocities. V2 is the velocity of the black hole 2, which is in rest. We actually do it from the frame of black hole 2, that is, it's in rest, and then V1 has some components there. So if we compute this integral, the integral can have some complete form. It's actually related, I mean, has some Bessel functions. We get some Bessel function there. And this result has some massless limit, smooth massless limit, which has the following form. And go beyond that we have also have 2 p.m. examples. That the previous one was the 1 p.m. example, and the 2 p.m. example is more involved. So we have some here we have some worldline propagator also, and this results to some by using Pesarini-Feldman reductions and standard dimensional regularization procedure, we can get the exact result of the impulse. But this integral, we actually has no complete form. So, but when we take the massless limit, it has some complete form that is proportional to 1 over b square. Okay, so now go to the radiation part. So for the radiation part, we have the following scalar radiation diagrams, and we have some graviton radiation that exactly comes from the presence due to the extra scalar fields. Okay, and the scalar waveform, yeah, we actually compute the waveform in time domain, and the time domain waveform we have to do some integral like this, and you have to choose some parameterization of in which direction we are measuring the radiated field. And here the kmu, here kmu is basically the external radiated momentum, and we have to have some on-cell conditions on it. When we have graviton, it has some k square equals to 0 on-cell conditions there. Okay, and after doing Feynman parameterization and the integral representation of the Bessel functions, we have this kind of expressions where this dy is basically nothing but the Feynman parameter. And again, this integral does not have any closed form. Okay. And here we take, in these computations, we take the scalar field to be massless. But now the question is, if the scalar field has mass, then what is the difficulty? Now see, we have some integral over, we have some Fourier integral there, because we are doing things in time domain. So for massless case, we have k square equals to 0 on-cell condition, but here we have k square equals to m square on-cell condition. So the direction of the propagation is basically now dependent on the radiated energy omega. Okay. And that is the main difficulty, because in the previous case we have some simple scalar simple Fourier transform, but now we have some complicated phase structure there. So it is very difficult to do analytic to find the analytic result out of it. So to make some progress analytically, so we take the stationary phase approximation, and in a scattering event, we expect some burst situation and around some radiated frequency. And the full waveform calculation for every diagram has this following form. And what we do is that we use the stationary phase approximation to get this formula. So once we get this formula, then life is simple, because now we have to do only the momentum loop integrals there. We don't need to do the Fourier integrals. So for example, let's take this diagram again, and this diagram is actually has this type of form, and now we have to do only the momentum integral there. Okay, and the momentum integral can be exactly computed, and we can have some result using in terms of Bessel functions. And again, we have some integral over the Feynman parameter left, because we don't find any closed form expression of this integral. In principle, one can compute it numerically, but analytically, at least at this stage, we start. Okay. So what next? So we need to go beyond 2 post-mean Gaussian, I mean 2 p.m. or 3 p.m. or 4 p.m. And we have to include the spin. So at least for one of the diagram we may compute is that this kind of diagram where we have two worldline propagators there. Then the computations is difficult, because the numerator of this Feynman integral is difficult. I mean, it has 16 terms. So this integral can be computed by IBP reductions and using this package by Lightfred. And what we find is that this complicated structure has very simple result there. And the master integral, and we have some, if we have some fixed number of propagators or irreducible numerators, then the master integral is fixed. But at least for this diagram, out of maybe 28 master integrals, only 2 will contribute there. And this master integral can be exactly computed. And after doing the master integral, we can compute the Fourier transform of it. But here we take, in these computations, we take m to be 0 for massless case. But if we have mass, then might be things are more and more involved. So for the future, definitely this analysis can be extended to higher PM orders, and higher PM orders means we have to do higher and higher loops. And if we take mass into account, then the IBP may be non-trivial. And then we have to do the master integrals more carefully, as Raphael mentioned in his first talk. And maybe we can use, we should investigate the whole analysis when we have some spinning black holes there. And also the analysis can be carried out for higher derivative gravity theories also. And we can also in principle take radiation reaction effect, because in our computations, we didn't take any radiation reaction effects there. Okay, thanks.
Thank you, Saptaswa, for a nice talk. So the forum is now open for the questions. Questions from the audience. You may just unmute yourself and ask the question, or raise your hand. Okay, before anybody else is asking any question, let me ask you one question. So, as you have shown that all this quantum field theoretical techniques are related to worldline sort of framework here. So,
Right.
and one of the key result is that this 1-point function is playing the key role. I mean, you don't need to go for 4-point function or 3-point function, 2-point function in the other side.
Right.
Everything is getting reduced to 1-point function. So my question will be that how this technique is sensitive to the kind of scattering of black holes, etc., taking place actually. So all types of scattering phenomena are included, or it's particular to
Yes, at least what I discussed
unbounded
is
orbits or bounded orbits, bounded
that
systems and unbounded.
definitely unbounded, because here
Unbounded.
some scattering even there.
Yeah.
But in principle, if we can treat black holes as point particles, because I mean, if we take neutron stars there, then you have to take the finite size effects, and the finite size effects can also be implemented there. I mean, in this procedure, but we didn't take it. We take it as point particles there.
So since you are taking post-Minkowski, and so I mean, is there any similar? Is there any formula like we get in standard quantum field theory, like scattering cross section, which because the massless scatterings are happening.
No,
So
the scattering, I mean, the external particles are massive, right? Because you have some massive black holes there. And you may have some radiation. The radiation is massless, because if it's a graviton, it's massless.
yeah, so when you are talking about radiation, yeah, so then this radiative fields, you can sort of somehow will there be any relation with the uh, so-called memory effect, etc., that we see in the far region?
That I have to
Because
think. I think it should be there, because it's nothing new. I mean, the procedure is new, but you can eventually uh, reconcile of the everything from out of there, because the procedure is for some quantum field theory techniques. But I think this something, I don't know, maybe it can take
so
soft
in
limits or
this so in this framework, you are assuming that be it Einsteinian gravity or beyond, there is some uh, uh, I mean some scattering states. They are there in the infinities, right? Null
right,
infinities,
right,
right?
right.
This is assumed. That.
Hmm.
So yeah, I think that may be possible to relate this.
Yes, yeah. Because it's ultimately a scattering process, and the scattering process in usual quantum field theory, what the scattering process, we have some path integral over the fields. Now we just represent the path integral over fields to the path integral over the word lines. It has some representation. That is the main difference. And as we have the path integral over the word lines, here actually is kind of the word lines are basically quantized, you can so called. I mean, although we are taking into account the classically solid.
I mean, can we get the quadrupolar formula of classical GR from here?
I think we can, because right here we
I
compute
mean,
the
should be, yeah.
left hand side of the Einstein equation, right? Because we directly compute the 1-point function of the not the right hand side. Exactly compute the 1-point function of the gravitational field. It's the way around.
Okay. Are there any further questions? If not, let us thank Saptaswa for his nice talk. And